Hi everyone, and welcome to 2.7, which is a continuation of confidence intervals for proportions. So if you'll recall, in the last lesson we looked at 95% confidence intervals for the population proportion, and we had this formula here, which was our point estimate plus or minus 2 times our standard error. Remember, since we don't know the population proportion p, we're substituting p hat in place of p. And the reason we're multiplying by 2 is because we are looking at two standard errors outside of the mean. And remember that that is 95% of the distribution. So let's say, though, that we want to become more confident. Instead of 95%, let's say we want to become 99.7% confident. If you'll recall, we are going to take our formula and in place of this 2, 99.7% tells us that we would want to be 3 standard errors outside of the mean. Okay, so if you'll remember the problem with the 830 millennials, where 315 had at least one tattoo. The value of P, our population proportion, our parameter, is the proportion of all millennials who have at least one tattoo, is really unknown. Okay, this is based on a sample that we took. So we're going to use the random sample of 830 millennials to estimate the proportion of all millennials who have a tattoo. So in other words, when we're looking for the proportion of all millennials that have a tattoo, we're looking for P, which is our parameter, our population proportion. Okay, so we want to determine a margin of error if we want to do a 95% confidence interval. So to do that, if we're dealing with 95%, we would multiply the standard error by 2. Okay, so we would take the number of millennials in our sample that have at least one tattoo, which is 315, divide it by the total in our sample. 315 divided by 830 is 0.38. That's our p hat, our sample proportion. We're going to take 0.38, multiply it by 1 minus 0.38, and divide that by the sample size. And then we're going to take this, which is our standard error, and multiply it by 2, and that gives us our margin of error. So this number in here is what you should get when you multiply by, or when you take the square root of all that stuff inside, and then the answer 0.034 is our margin of error. And we're going to take p hat, 38% or 0.38, plus or minus 0.034. So basically that tells me that 38% minus 3.4% to 38% plus 3.4% would give me an interval. And I'm 95% confident that the percentage of all millennials, P, the population proportion, with a tattoo is between 34.6% and 41.4%. So if I want to become more confident, I'm going to take that 2 and replace it with a 3. So really what I would have here is p hat plus or minus 3 times the standard error. And remember, that's going to give us our margin of error. So here I would just have 0.38 plus or minus my margin of error, which will be calculated by doing 3 times 0.017. And then that is going to give me, I believe, 0.0505. Okay, so as you can see, as we become more confident, what happens to our interval? It's going to get wider. And if you visualize that, like on the normal model, okay, here's your mean, which is P. Okay, right now we're trying to figure out what that is. And then we have 3 standard deviations in either direction. So when we were 95% confident, this was our interval. But now we want to be more confident. So now this is our interval. And as you can see, the interval is much wider. So even though we have a better chance of capturing the true proportion, we are not as we're not as precise now. So it's equivalent to like if you had a park that was this small and I said I buried a treasure in it, go find it, compared to a park that was this large, right? The larger park has more area, so I'm covering more area there, but it's less precise in that it's going to take you a longer time to find the treasure. Okay, so I just basically worked all of that out for you. But if you were to calculate that actual 99.7% confidence interval, 0.38 plus or minus 0.0505, the problems above this just kind of take you through the steps. If we do 0.38 minus 0.0505, we get 0.3295, and then 0.38 plus 0.0505 gives us 0.4305. So if you compare this interval here to the interval we found using the 95% confidence, you can see that it is much wider, because our lowest value for 99.7 is 32%, approximately 33%, all the way up to about 43%. So if we were asked to interpret the interval in the context of the problem, we could say that we are 99.7% confident that the percent of all millennials with at least one tattoo is between about 33% and 43%. So what's an advantage of that interval over the 95% confidence interval? A wider interval can capture the true proportion. Okay, if we wanted to be less confident, our interval will be smaller, but there's a chance that we won't capture it. The disadvantage of the 99.7% confidence interval is that it has a larger margin of error and therefore it's less precise. So in general, the more confident we want to be, the larger the margin of error will be, since we have to reach out farther to capture the population proportion. So if we wanted to be 100% confident, the percentage of all millennials who have a tattoo is between 0 and 100%, but that's not very helpful, okay? That's like if you came up to me and said, how did I do on my midterm? And I said to you, well, I'm 100% confident that you got between a 0% and 100%. You're not going to leave feeling very confident about our conversation, right? But if I said to you, I'm 90% certain that your score was between an 80 and a 95, you're going to feel much better about that conversation. Okay, so my interval is much smaller, but I'm less confident. So it's all about finding a sweet spot. So something important to remember is increasing the confidence level will make it more likely that P falls in the interval, but the interval will be larger, making the statement less precise. So we can use any confidence that we want. If it's one of the percentages used in the empirical rule, then that's really easy for our formula. However, let's say we want to be 90% confident. What value would we use? We have to rely on technology or tables to help us. what we're going to do is we're going to find something called a critical value. And right now, we're going to denote that using z sub c, okay? And it's based on the normal distribution. So to find the critical value or critical z for a 90% confidence interval, we can't use our empirical rule because our empirical rule only includes 68, 95, and 99.7. So lucky for us, on our calculator, we have a function called the inverse norm, which you can find when you go to second vars. It's in the same place as normal CDF, okay? So if we want to be 90% confident, what we have to remember is that there's 10% uncertainty, right? 100% minus 90% leaves us with 10%. Since the normal distribution is symmetric on either side, I'm going to divide that 10 by 5. So each side would have 5%. So if I want to find the critical value for 90%, I'm not going to type in the inverse norm of 0.05. I'm going to type in the inverse norm of 0.95, because if you type in 0.05, it's going to give you the critical value here, which is fine, okay, but it'll be negative, and you can't use that when you're trying to find your confidence interval. You have to use the positive version. So you would just need to make it positive instead. So here's the value for but if you think of 5% as the top 5%, and then here's some important
you're
facts.
in the 95th
when
percentile,
the z-score is negative, it just means that value is below the mean. You'll get a positive.
If z is positive, it means that value is above the mean. So when you get a z-score of 0, it just means that value is equal to the mean.
And then vars, and then number 3, inverse norm.
Let's next talk about normal
0.95,
distributions.
Enter,
which is a very important distribution in
1.64.
So,
okay. So what that means is like
the normal distribution is a model that we use
or 3
that helps us to precisely describe where a value is.
That's
in
also telling me on the normal model.
We can make a lot of estimations.
If this is 90%
we
here,
can calculate
the
probabilities,
the cut
percentages
value for 95
using the normal model.
Percentile would be 1.64.
Most of you will have seen this normal model before.
And I'm
it's
actually
bell-shaped, where it's a bell curve.
Here. Since that's what the
and
book
it's
does.
appropriate to use when modeling the behavior of distributions that are unimodal, which remember means one mode, and fairly symmetric.
Okay.
So we say fairly symmetric because in real life, there's not going to be a normal model that's completely perfectly symmetric.
We
where
know
you can
that
cut it in half down the middle,
critical
and it's the same on both sides.
On the left would be
we have lots of models and statistics,
and then this is just
but this one particular type called the normal model is very useful because we can make a lot of estimations from this model if we know some clues.
What percent of the sample proportions are between
values? We need to know the population mean, and we also need to know the population standard deviation.
So 90% of the area under the standard normal.
Other times we won't have it, and we'll have to estimate
because of this, the critical
sample
value for the
standard
90%
deviation.
level of
But that's for
confidence.
another lesson.
Again, we're going to use the positive version.
So here we have a normal model, okay, and it's representing the heights of randomly selected men
from a table.
If you were to take a large group of men and you were to create a histogram, it would come out to be
and
bell-shaped.
We're looking for
there's going to be
90%
a mode,
confidence,
where most men are this certain height,
which is,
and then you'll have men that will be taller, and men that will be shorter,
go all the way down,
and men that will have an average height. So the average, as you can see, is right in the middle. Okay? And that's mu. That's the population average. That's the average height of all males, which is telling me it's about 69 inches.
Okay.
And then it says the standard deviation is sigma
for approximating normality for
so
confidence
if you
intervals,
take a look at these values,
as we use for
69 falls right in the middle. Okay, that's where mu will always go.
Randomly selected
and then 69 plus 3 gives
the population
me 72.
Should be greater than 10 times the sample
that
size.
tells me that's one standard deviation above the mean.
Larger than the population.
72 plus 3 gives me 75. And then we also have our success failure. That tells me that
again,
is
you're using p hat
2 standard deviations above the mean.
So let's try this example here.
And 75 plus 3 is
devoted to
78,
science fiction,
which is 3
books,
standard
television,
deviations
and
above the
movies
mean.
focus on imaginary
If I
stories
go
and
backwards
topics like
now,
outer space
mu is
and
69, so
futuristic
69
technology.
minus 3
A science
gives
fiction
me
website
66.
made an important announcement.
So this is
The announcement
one
was
standard
about college
deviation
students' beliefs
below
about
the mean. So remember, we're going to put a
extraterrestrial
negative there.
The website claims
66
that the proportion
minus
of college
3 is
students who believe that
63.
extraterrestrials
So that's going to
have
be
visited
2
Earth is
standard
equal to
deviations below.
0.06,
And then
6%.
63 minus 60 is
Suppose you
63
wish to
minus 3
investigate
is
this
60,
claim by
which
doing
is
your own
3
study
standard
of a
deviations
randomly
below.
selected sample
Okay, so
of
what does
Valencia
this tell
college
me?
students.
Well,
You take
I
a
can make
random
certain
sample of
predictions
250
knowing
Valencia students, and you
between
find that 45 believe
what
that
standard
extraterrestrials have
deviations
visited Earth.
this
So
any
if I want
male
to find my sample
height would
proportion,
fall.
my p-hat,
So if
I'm going
you're
to take the number of
male
students
that's
that
70
believe in
inches tall,
extraterrestrials,
I could
and then divide
approximate
that by my sample
how many
size.
men
So when you
would
divide
be taller
45
than you,
by 250,
or how many men
you
are
get
shorter than you.
0.18. So 18% of my sample
And we
believe
use this
that
rule, it's called the
extraterrestrials have
empirical
visited
rule,
Earth.
which we'll talk about here shortly.
I'm going to go through
what
my
you should do now is
three
pause the
criteria.
video
The
and
first
read about
is,
the
does it say
following
anything about
characteristics
random? And it
of
does.
the
It says
normal
a random
distribution.
sample of 250.
So here are some of the
Valencia
characteristics that you
students.
need to remember. The mean and the median are equal. So right here we have our mean, and that's also where the median is. And
in
half
my
of the
second
values
condition,
will fall
I'm gonna do
above the
10
mean and median, and half will
times
fall
250,
below.
which is 2,500.
The normal
and it's
curve is
reasonable
bell-shaped
to
and
assume that there's
symmetric
more
with
than
respect to the mean.
2,500 students.
So if we were to fold
attending
down the
Valencia
center
College.
along the mean,
And then for
it
my
would
third
be
condition, I've got
pretty much the same
n
on either
times
side.
p hat, and my p hat is 0.18.
The area under the
and
normal
we need
curve
to check to
is
make sure
1
that's greater
or
than or equal to 10.
100%. So theoretically, this
n
curve goes
times
on
1 minus
forever
p hat,
towards
and 1
positive
minus
infinity
0.18 is
and
0.82.
negative infinity.
And also we want to
Okay,
make sure
but the
that that's
area
greater than or
under
equal
it,
to
the
10. And
shaded
if we do a
area,
really quick check,
would be
10%,
100%.
right? If I'm not even talking about 18%.
The
10%
normal
of
curve,
250
as I
is
said,
25.
extends
So
endlessly
18%
in
is
both
much bigger than
directions.
10.
Okay, but as you
and
can
that
see,
also goes for
the closer
the
you go
250
towards
times
positive
the
infinity or
0.82.
negative infinity,
Okay.
the
So
area
next I
gets
want to find my
smaller and
standard error.
smaller and smaller.
And remember, when you're doing hypothesis tests, you're going to multiply.
And the normal
you're gonna
curve
take the square
changes
root
its
of p
curvature
times
from
1 minus
upward
p
to
over
downward
n.
and vice versa
But we don't know
at
p.
one standard
We do know
deviation
p hat,
below and above
which
the
is
mean. And
0.18.
these are called inflection
So I'm going to multiply
points.
0.18 times
So
1
this value
minus
here is
0.18
just whatever the mean
and
is
divide
plus
by
1
my
standard
sample
deviation.
size,
So in our
which is
last
250.
example, it was
And when you
69
do that,
plus
you
our
get
standard deviations were 3.
0.0243
So 69
for your
plus 3
standard
gave
error.
us 72.
So I want to find
on.
the margin of error for 98%.
A normal
confidence
distribution
interval.
is
So
determined
if
by
we
its mean
visualize
and
this,
standard deviation.
Okay. We've got
So one normal distribution might
98%,
have a mean of 23,
right, which is
like
2%
in this
away from
normal distribution,
100%.
because that's the middle
So
of
I got to split
distribution
it.
C.
I have 1%
and a
1%.
standard deviation of 1.
So if I want to
23
find
plus 1,
the margin of
24
error,
plus
I need
1,
to find my
20,
z critical
5
value.
plus 1.
And to
and
do
then we're
that,
at 3 standard
I've got to do
deviations.
the inverse
Another
norm
distribution could have a mean of 15 and a standard deviation of 1.5. So I can tell
So
here
100%
that the middle
minus
is
1%.
15.
You could do
and
the inverse
I would
norm
add
of 0.01,
1.5
but
to
it's
get
going to
to
give
my
you a
other
negative critical value. Just remember to make it
values.
positive. So when we do that, we
So
get like 2.33.
normal curves can have many different values for the
You
mean
can also
and
go to the
standard
tables.
deviation.
You have to go to the
Fortunately,
t-table.
all normal
You're going to
distributions
find
have the same
99%,
relationship
which is
between
right
the
here.
area
And if you
and
scroll
the
all
number
the way
of
to the
standard
bottom,
deviations from the mean.
98%.
So this is
we're
called
doing.
the empirical
If you scroll all the way to
rule.
the bottom, you get
And what the empirical
2.326,
rule
which is
tells
like
us is
2.33.
if a distribution is approximately normal, so
So
bell-shaped
to find the
and
margin of
unimodal,
error, remember I
then
need to
that means
multiply
that
my z
roughly
critical
68% of the values will
and
fall
when I do that, I get
one standard deviation above and below the mean.
So that's my margin of error.
So if you take into account male height,
so
I
what does
can
that
say
mean if I was to
roughly that about
interpret
68%
that? Think
of
of that as a
male
percentage,
heights
and it's
would
just
fall
the percentage of all
one standard
Valencia
deviation
College
above
students
and
who
below
believe
the mean.
extraterrestrials
So
have
if you go
visited
back
Earth
to your diagram,
is
one standard deviation above and below the
18%
mean
with a margin
would
of
be
error
here.
of 5.7%.
So this tells
So
me that
means give or take,
68%
okay?
of males
So if I was
fall
to
between 66 inches
calculate
and
that
72
98%
inches
confidence
tall.
interval, that's going to be my p hat.
And
plus
if I
or
was to
minus
continue
my
going
margin of error,
out
which was
another standard deviation, 95% fall
0.05566.
within 2 standard deviations.
So to
of
calculate
the mean.
that, I'm going to
And
do
even
0.18
further out,
minus
99.7%
0.0566,
fall within
which is going to
3
give me
standard
about
deviations of the mean.
13.2%.
So that tells me
and then
that
18% plus
if I change colors here,
0.0566
95% of males will fall between 63 inches and 75 inches.
To interpret that
tall,
we would say we are 98% confident.
Since I can't fit it above, I'll put it here. 99.7% of males will fall 3 standard deviations above and below the mean. As you can see here, anything beyond 3, the area gets really, really small. So it's very unusual to have a male
visited
to have a height of more than 78 inches or less than 60 inches. It would be unusual or rare to see that. And pretty soon we'll be able to calculate those probabilities using either the empirical rule or using some other calculations that we can do using tables and the calculator.
The proportion of college students who believe
so you want to remember the empirical rule. It's really important. 68, 95, and 99.7%. And again, it just means that roughly
or 6% in our interval.
68% of the values will fall within 1 standard deviation of the mean.
Because
95% of the values will fall within 2 standard deviations of the mean. And 99.7% will fall within 3 standard deviations of the mean.
Okay, so the next problem
is something else that's important. As I was saying, the further out you go on the curve, the smaller the area gets.
And then
the empirical rule tells us that only about 5% of the values are more than 2 standard deviations from the mean.
Reach out to me or
in other words, what they're saying is,
you all have a great rest of your day.
If this right here, this area represents 95% of the values, we know that the curve is 100%. So if I do 100% minus 95%, I'm left with 5%. So the 5% represents this tail and the area under this tail. And of course, forever and ever, right? Because it goes on forever. So that would tell me that 5% of the male heights would be more than whatever that value was. I think it was 75. So more than 75 inches and less than 63 inches. Okay, so only 5% of individuals would fall into that category. So because of this, we say that values that are more than 2 standard deviations from the mean are unusual. And that's important. Okay, even more unusual beyond 3 standard deviations, but 2 is kind of the cutoff. So if you are more than 78 inches or less than, or no, it was, 78 inches or you're less than 72 inches, it would be very unusual. Okay, I think those were the values. I want to make sure. Yep, 78 and 63. Sorry, 75 and 63. So this is 75 inches and that's 63 inches. Okay, so any males more than 75 inches and less than 63 inches would be considered to have an unusual height, which just means it's rare to find that height. Okay, so many populations are approximately normal in their distribution. Let's go back again and look at the population of all men's heights. So we already kind of did that. We know that the mean went right in the center. That was 69 inches. So I'll do this again to make sure we're clear. Our mean is 69, and because the standard deviation sigma is 3, we're going to add 3 each time to get 1 standard deviation out. So 69 plus 3 gives us 72 inches, plus 3 is 75 inches, plus 3 is 78 inches. And then 69 minus 3 is 66 inches, minus 3 is 63 inches, and then minus 3 is 60 inches. So again, anything outside of the 95%, so anywhere this way or this way, is considered unusual or rare to find that a height of that size.
Okay, so we have all our sketches. How do we find the actual percentages now? Okay, so we're gonna use our curve. So looking at the previous sketch and using the empirical rule, what percentage of men's heights will be between 66 and 72 inches? So we know that 66 is here and 72 is here, and they're both 1 standard deviation above and below the mean. So remember that 68%, it's kind of hard to see that, so let me write it like this. 68% falls within 1 standard deviation above and below the mean. So we can say that the percentage of men's heights that will be between 66 and 72 inches is 68%, approximately. Okay. 13 is saying, what is the probability that a man is between 66 and 72 inches? So the probability, remember, of an event is just the likelihood that that event will take place. Or in other words, the likelihood that a man will have a height between 66 and 72 inches divided by the possibility, the total possibility that they could. So our likelihood is 68% divided by the total, which would be 100% of all males. So that's just 68%. So when they ask you, and this is very important, when they ask you for what percentage and what probability, these are basically asking you the same exact questions. And that's very important to know because they're going to use those words interchangeably. Okay, the probability that a man is between 66 and 72 inches tall is the same thing as saying what is the percentage of men that will be between 66 and 72 inches tall. Okay, I'm going to let you all try numbers 14 and 15. And we kind of already labeled the diagram there for number 16. So let's work out some other problems here. And you all can answer number 17. Let's look at a new problem, number 18. So you'll want to pause the video and read the problem and then unpause it when you're ready. The speed limit on a road in town is 35 miles per hour, and a device used to measure the actual speed of cars traveling on the road finds the distribution of speeds to be approximately normal, with a mean of 35 and a standard deviation of 5. Answer the following questions using the empirical rule. So we want to label the normal curve below with the appropriate mean miles per hour and 3 standard deviations in either direction. Okay, and that's generally going to be the rule that we're going to follow for the remainder of the course. We want to, let's see, answer the following questions using the empirical rule. So we want to then, below that scale, label the speeds with the appropriate z-scores as you did in question 20. All right, so if we look at the problem, they tell us that we have a mean of 35 and a standard deviation of 5. So remember that this is actually mu, and this is sigma, okay? Mu is, again, the population average or population mean, okay? So you're taking into account all these cars whose speed was taken, so that's your population. And then we found the standard deviation as well. It was given to us in this problem. This is our population standard deviation of 5 miles per hour, okay? So we know that the mean goes in the middle because it's the average. So 35 is going to go in the middle. And since my standard deviation is 5, I'm going to add 5 to 35, and I would get 40. And that represents 1 standard deviation above the mean. Okay, 35 minus 5 is 30. That would be 1 standard deviation below, and so on. Okay, I'm going to go back to the mean. 35 plus 5 gives us 40. 40 plus 5 is 45. 45 plus 5 is 50. So this is 2 standard deviations, 3 standard deviations. And if I go backwards, I'm just going to subtract 5 each time. So we know that this 25 miles per hour is 2 standard deviations below, and 20 miles per hour is 3 standard deviations below. So there's my normal distribution set up according to this problem. And by looking at it, I know that my mean is 35, and these are your z-scores. If you're a car that's traveling 40 miles per hour, right, you are 1 standard deviation above the average speed. Okay, so these represent the z-scores. Okay, so that would just mean z equals 1, and this means z equals -1. So if you're a car and you're traveling 30 miles per hour, you're actually 1 standard deviation below the average speed of the cars on that road. So then answering these questions, what is the probability that a randomly selected car on this road is traveling below 25 miles per hour? So think of this right here is our 25, and I'm going to put a little flag right here. We want the probability that any car randomly selected, right? So any car would have an equal chance of being chosen, that car is traveling below 25 miles per hour. So I need to use my empirical rule to figure that out. So if you'll recall, anywhere from 25 to 45 is 2 standard deviations above and below the mean. And using the empirical rule, we know that that area in between the two flags is 95%. So if I take 100% and subtract that 95%, it's going to leave me with this area and this area. So in other words, if I do 100 minus 95, I'm really subtracting away this piece right in here. So it's going to leave me with 5%, right? But that represents either side of the flag. We only care about this side. So I need to divide by 2 because remember, one of the properties of the normal distribution is that it's symmetric. It's the same on both sides. So these flags are the same distance from the center. So I'm just going to do 100% minus 95%, which gives me 5%. And then I'm going to have to make sure I take the 5 and divide by 2, which is 2.5%. So the probability that a randomly selected car is traveling below 25 miles per hour is actually just 2.5%. Now I want to know, what is the probability that a randomly selected car on this road is traveling between 35 and 40 miles per hour? Okay, so I'm going to take this this picture here, and I'm just going to copy paste. Okay, I'm going to shrink it down, and I'm going to, let's see if this will work. Let me put that back a second. Let's see. Okay, instead of redrawing, I can just go like this, and then maybe I can erase that stuff. Okay, so I'll do the best I can getting rid of this stuff. All right, I don't want to mess with it too much, but hopefully you can all see now. So now I'm looking for 35 and 40 and in between, right? So let me use a different color here. So 35 is here and 40 is here. And there's a couple ways you could do this, okay? So one way that stands out is, if you'll remember, between here and the furthest orange flag, so here, that's 68% of the data. It falls within 1 standard deviation. But I'm only looking for the probability that someone traveling on that road is going between 35 and 40 miles per hour. So using one of the characteristics of the normal model, I know that it's symmetric.
So all I would have to do is divide this 68 by 2 because this area is the same as that area. And 68 divided by 2 is 34. So approximately 34% of cars traveling on that road will be traveling between 35 and 40 miles per hour. Okay, we know that the middle 95% of cars are going to be 2 standard deviations above and below the mean. So we know they're going to be between 25 and 45 miles per hour. And almost all of the cars on this road would be traveling between 20 and 50 miles per hour. Anything beyond those two values is extremely rare. In this book, we say anything above 2 standard deviations is rare. So the probability that someone is driving more than 45 miles per hour on that road would be rare. And the probability that someone is traveling less than 25 miles per hour would be rare. So if you think about it, anybody going above 50 or below 20 would be extremely rare. So mostly everybody, 99.7%, are traveling between 20 miles per hour and 50 miles per hour. The reason we can't say 100% is because, remember, the whole curve represents 100%. So that's the end of this lesson. We're going to see more of the normal distribution throughout the entire book. So it's really important, this section, that you understand z-scores and also the normal distribution. So please go back over the notes and go over the summary here. These are highlighting the important things that you need to know. And then there's the homework at the end. This is the bare minimum of practice that you should do to feel comfortable with this section. If you need more practice, I can provide more problems for you to try. But doing these problems is, again, the bare minimum. If you've never seen this before and you need practice doing it, because a lot of what we're going to do going forward will relate to z-scores and the normal distribution, and your understanding of it is critical to understanding the rest of the course. So please reach out to me if you have any questions, and I hope you all enjoy the rest of your day.